As John said, I'm going to talk about the growing threat from insecticide resistance. That's actually a title that I was given by HGCA, so don't panic, not yet anyway. Right, a little bit of background. The key to managing resistance is having a diversity of pesticides available. Diversity, it's the spice of life, it's also the spice of management. And if you don't control aphids in this case, you can end up with problems like this. This is on potato. I haven't got any pictures of oilseed rape, that's why I given you potato, but when the aphids get out of control, they're resistant, you can't do anything about them. They can essentially suck the life out of the plants. They can also spread viruses. There is a paradox. A lot of aphids experience pesticide applications, treatments, but not all of them evolve resistance. The main players in this country, Persicae, Phoidon humuli, the hop aphid, and Aphis gossypii, which is restricted mainly to glasshouses. There's those where we think there may be something going on, including Cytobium aveni, and I'll talk about that towards the end of my talk. And finally, those that don't appear to involve resistance, even though they've experienced application. So it's an interesting evolutionary question, why some are better than others. The questions that get asked about any new compound that comes on the market is, will resistance arise? How fast will it arise? You know, how quickly will we see it? What are the practical implications? Is it localized? Will it stay around? And how can we stop it, resistance evolving? The message that obviously I want to give, and it's obvious really, is that no synthetic insecticide is inherently immune to resistance, although some seem better than others at withstanding the evolution of resistance. And in theory, all pests should be capable of acquiring resistance. You know, they carry DNA, you have mutations, and you should hence have resistance evolving. But as I've shown in the previous slide, it doesn't always happen. I'm going to start by talking about the main player for aphicide resistance in the UK, which is Mysis persicae, the peach potato aphid, which goes on a range of crops, including oilseed rape. It's evolved resistance to quite a few compounds, classes of compounds, the OPs, the carbamates, and the pyrethroids, and these are conferred by esterase and what we call MACE and knockdown resistance. Esterase is a metabolic type mechanism, and MACE and knockdown resistance a target site. I won't go into the details of those. For the last 3 years, I've been working on a project, a link project, which is partly HGCA funded. You can see the other players, the partners in this project. So it's a big consortium looking at Mysis persicae and a few other aphid pests in the UK. And the UK seems to have got hidden, so it is the UK. And a little bit in Europe, keeping a watching brief on what's going on elsewhere, because it could have an effect, have an influence on this country. So let's start off with some data. Going all the way back now to 1996, we've been collecting field samples from a range of crops and looking for the presence, in this case, of the MACE mechanism. Now, MACE gives resistance specifically to Perimicarb. Aphox is one of the trade names. And these bars are simply showing samples, the frequency of samples that contained at least one of these resistant forms. So we first saw it in 1996. It then fell away, but recently we've really been inundated with these MACE forms, and as a consequence of this, we've sent out released alerts and in guidelines to say really you should not be using Perimicarb against this particular species, aphid species. KDR, recently it's fallen a bit, but there's a twist on this. KDR gives resistance to pyrethroids, and I'll talk a little bit about that later on. But you can see we have the ability to monitor for these mechanisms using, in this case, DNA diagnostics. Interestingly, most of these individuals are heterozygotes. They're diploid, Mysis persicae is a diploid organism, and these individuals tend to just carry one copy of the resistance gene. That's enough to confer resistance to the compounds that have been applied. At Rothamsted, we look after a network of suction traps around the country, and aphids get sucked into these. They're upside down vacuum cleaners essentially, and then they're sorted into species, and some of them are tested, in this case Mysis persicae, some of the sites for the mechanisms. And here we have the sites we've been testing over the last few years. geographically around England, and this is the frequency percentage of mace forms in those. And you can see how mace has really taken off over the last few years, and this is 2011. So basically the suction trap data back up the field data. Mace is a very common mechanism in this species. KDR, we also look at sites for KDR, and 2011 you can see, it doesn't seem too high actually, but there is a twist to this, and I'll talk about this towards the end of the talk. And just to show how the data match up, we're showing the suction traps versus the field samples. A good agreement there, and not so good for the 2011, but it's not the end of the sampling yet. We've still got some samples to test. So there we have the ability to monitor for mace and KDR, which are important mechanisms in this species for resistance to perimecarb and pyrethroids. Okay, another mechanism we do look at, but specifically at Rothamsted, because we don't think it has an awful lot of importance nowadays, is esterase resistance. It's a metabolic mechanism, and the R2 and R3 forms have high levels of this resistance, and it gives resistance specifically to the organophosphates. And we've been keeping a watching brief at Rothamsted for this, and you can see over the last few years these forms have pretty much disappeared, and we think it's in part as a consequence of the phasing out of organophosphates and fitness costs imposing themselves on aphids that carry the high levels. In 2011 we found one R2 aphid. So in theory, if we had a resistance problem and this pattern continued, we could fall back on the OPs. Now I know that's not a great option, but when you're firefighting it could be useful. Okay, what about resistance to the neonicotinoids, which are now the biggest sellers in the world, and other newer compounds which are used for controlling aphids, and Myers-Persky included? Right, we've been monitoring going back to 2004, and this graph is essentially showing the percentage of samples that have contained aphids that have the ability to walk. What we do, we dose the aphids, live aphids in this case, with a screening dose of imidacloprid as a representative of neonics, and after 72 hours we come back and ask the question, how are they? So they're either lying on their backs or dead. They're capable of walking, which shows they have low-level resistance, or they're able to reproduce, which would suggest that they are highly resistant. And you can see in 2011 we found very few samples with these mobile forms in. So the message is, over the years, the frequency of these mobile forms has not gone up. So that's good news. What it's telling us is what we're doing in the UK at least, with spray applications and seed treatments, is not selecting for higher levels of resistance, which is a very important message to pass on. And another very important message is that we have not found any highly resistant aphids, those that are capable of reproducing, which we call these NIC-R++ forms. And I'll talk about those in a moment. Also, the good news is for other novel compounds which are used as alternatives in alternative sprays to neonics, pymetrine and flunitramide, plenum, one of the trade names, and topiki for flunitramide. We haven't found any shift in those either. So it's good news for the neonics and those other compounds, at least in the UK. Okay, right, a graph showing the mean January-February temperatures going all the way back to 1965, and you can see that overall the winters are tending to get warmer, which is indicative potentially of climate change. 2009-2010 was a pretty cold winter, at least in January-February. Interestingly, the last winter that's just gone fell very much on the line. Now, a lot of you are thinking, well, it was cold. It was cold in the first half, but the second half was relatively warm, January-February. So this actually is a very useful winter to allow us to look at how this affects our predictions. The insect survey make predictions on the first flights of Myers-Persky, which obviously ties in with whether or not there's a higher virus risk, because aphids flying into a crop earlier would have higher virus risk for the crop. And we've made various predictions. So on the basis of the January-February temperature, it was 5 degrees was the mean. But going to the two coldest months, which was December, January, it's actually below 2 degrees, which made a big difference in the predictions for virus. And this slide should have been hidden, but it's showing you the results straight away. So January, February, we had predictions in May, April, while the 2 coldest months pushed it right back. Basically, we had a difference of about 6 weeks in predictions. And Richard Harrington was sweating on this because he was worried about whether or not he should be using the 2 coldest months or not. It turns out the actual flights were in the middle, so a bit boring, I'm afraid, but that's science for you. But at least years like that allow us to test the system to see how much, if it's the coldest months or January, February. And that one pops up there for some reason, I don't know why. Okay, right. What we can do with Mysis-Persky is we can look at their genotypes as well, their resistance genotypes, as I've just mentioned. So here we have, in 2009, the actual percentages of aphids that we found in England. And it turns out, surprise, surprise, that the mace forms were the commonest. Interestingly, in 2010, we found a very simple proportions, suggesting that they're very stable. And 2011 so far, we've seen that. Now, this suggests that the aphids we currently have in this country are very well adapted for living in this country, and hence the frequencies aren't changing. And even a cold winter that we had, the last winter, and last winter but one as well, don't seem to have perturbed that. So they're very well adapted to life in cold weather. And I'll stress that in Mysis-Persky we think they overwinter as active forms. They don't go through the egg form, which is highly cold tolerant. They actually are active forms on crops like oilseed rape. Right, now, the additional thing we can do, we can DNA fingerprint aphids. And this work is done at the moment by Brian Fenton up at the James Hutton Institute. And he's been looking at the aphids we've been collecting in suction traps and on field crops to see what genotypes they carry. And it turns out the population of Mysis-Persky in England and Scotland is very narrow genetically. We have what we call C types, those that carry KDR, O and P types that carry mace, and those that carry other combinations. So that was the suction traps in April, July, and that was the field crops. So again, these forms are highly stable, we think, the mace forms, and there isn't a much genetic variation coming in from other countries. Resistance to neonics. Now, I mentioned these, we've been monitoring for resistance and looking at what the profile is in the UK, and we do this by a screening assay. And up to a few years ago, we just divided aphids up into 3 types. Those that were fully susceptible, those that we called the low resistant forms, and those that had slightly higher resistance in these topical assays, NIC R+. We also can look at aphids and look at how they behave systemically. So you don't dose them directly. You have aphids on leaves. You put the leaves into the solution of the insecticide goes up into the plant, and then you look at how they respond. And interestingly, then the resistance factors plummet. So the actual how you apply an insecticide is very, very important, we think, for the resistance factor. And finally, we've been doing some work actually in our field simulators on whole plants in a more realistic situation. And suffice to say, the R and R+ individuals behave very similarly, like with the systemic test, while the susceptibles are more affected. So this actually has a message. What it's telling us is how you apply your insecticide in the field, either as a foliar or maybe as a seed treatment, could have a big influence on the selection pressure and the resistance risk. Right, great moments in evolution. I think there has been a great moment in evolution, and it had happened in aphids. It happened in other species with neonics in the past. Tobacco whitefly took about 6 years to evolve full resistance. Glasshouse whitefly about 6. Colorado potato beetle a bit longer. Brown planthopper, which is a pest of rice in Asia, a bit longer. Up until about 19 years, we didn't see any resistance to neonics in any aphid. However, we have now found it, and we found it in southern Europe. This is essentially a graph showing the response on a log scale of the 3 types, the susceptible, the R and the R+, to imidacloprid. And this is where these resistant forms sit. And remember, it's a log scale. And these individuals, although some of them are affected, are still capable of reproducing. We now have control busting resistance. But of course, the previous slide showed we haven't yet seen it in the UK, so it's good news. There's no colour. There are lots of different colours of aphids, but unfortunately resistance isn't colour-coded, so we can't use colour. In the past, mace aphids were red, and people were saying, I've got red aphids, there must be mace, but unfortunately we can't do that. And this is how they look in an assay. These are the R plus with 100 ppm in imidacloprid. They've keeled over. These are the R plus plus at 100 ppm, and they're happy as Larry. They're reproducing, so they are highly resistant. Back to the systemic test. Interesting, when you look at these highly resistant ones, the resistance factor is pulled back. So again, it suggests that how you apply the insecticide can influence how resistant these aphids are. This is because there's an element of behaviour involved here. And finally, we've done some work on these highly resistant forms in simulators. So these are responses, fitness, producing nymphs up to 2 days and 3 to 5 days. And these are the previous types. So pretty good control with full rates of pesticide, of imidacloprid, clothianidin, thiamate. And that's where the resistant ones fit. And this is relative to the controls untreated. So they, in effect, they're immune. So if they got potentially onto crops in the UK, they'd cause a lot of trouble. However, the good news is they are still in Europe, Southern Europe, France, Italy, places like that, but they've only ever been found on peach, which is an interesting question. Why should this be? Well, I've taken these aphids, and in fact different clones of these highly resistant ones. Interesting, they don't carry mace, but I think they will in the future because sexual reproduction will mix up the genes. And I put them on various crops, and so far I put them on these crops. So we've gone on to potato, onto oilseed rape, onto cabbage, onto lettuce, and onto broad beans, and they transfer very well onto those. So there's no reason they should be restricted to peach. What it's telling us is that they get onto these crops, and maybe these crops in this country, they should do very well, and they will be highly resistant to neonics. And finally, what we do with any new mechanism is we look to see if it's got an Achilles heel, whether it's got any fitness costs. And essentially what we do in one respect, look at behaviour, we can put alarm pheromone near to the aphids and see if they respond, because if they respond well to alarm pheromone, they're probably quite good at avoiding attack by parasitoid wasps and predators. And this is just a range of the responses of the different types, SR, R+. And you're not going to see this very well, but it's right at the bottom. Unfortunately, the R++ aphids are very good at responding to alarm pheromone, which suggests that they should be very good at avoiding predation. So that shouldn't be their Achilles heel. We don't know how well they will do in the winter. That would be the other question, but it's something we need to look at. And finally, for the neonic resistance, any new microsat type is allocated, if it's fairly common, a new letter, and we've got now up to Q and R, and this is their resistance profiles. Now, Brian Fenton up in Scotland in 2010 found some new types, and we thought, well, if they're new types, they possibly come in from Europe, and maybe they could be neonic resistant. The good news is that they all came out fully susceptible, homozygous susceptible. But we do have the ability to take this DNA test and look at the DNA of any new types that come in to see if they are resistant. So again, we're trying to stay ahead of the game. And to finish off, I'm going to talk about what appears to be another great moment in evolution. A lot of you probably heard about problems controlling Cytobium aveni with Lambda cyhalothrin and other pyrethroids this summer in cereal crops. And I got a phone call about this from an agronomist who asked, could I do anything about it? Well, we tried doing some bioassays, but the quality of the aphids wasn't very good. However, what we did do, and I gave these aphids to a colleague of mine, Martin Williamson, he looked at their DNA and he looked at a KDR mutation. That's the mutation in Meissner's persecuted gist that confers resistance to pyrethroids, and he's found it. Now, this was in a few samples. A few samples, they were from Cambridgeshire. However, I've spoken to Martin this morning, and he's done some recent tests, and we found it again in association with control failures. So KDR is in this species, and we think it confers resistance. What we need to do now is take live aphids and do bioassays to see how big the resistance factors are. So far we've only ever looked at their DNA. Okay, to sum up, Significant resistance to neonics, pymetrine and flow emitters has not been found in the UK so far, which is good news. Mace-resistant aphids are very common, so hence perimecarb should not be used. KDR resistance appears to be overall on the wane. However, Martin Williamson has also looked at another target site mutation. It appears that the O and the P types, those that carry mace, although they don't appear to have KDR, do have resistance to pyrethroids, and that's probably why they're so common. We want to do more work on that. So there seems to be another mechanism knocking around in the system. Small and large-scale assays of resistance factors suggest that how you apply the insecticide is very important, how it influences the evolution of resistance. We've only ever seen control-busting resistance to neonics in Europe, but it is moving gradually further north, and that's what happened with mace in the past. And the KDR mechanism has been found in grain aphids in Cytobium movini, and again we want to do bioassays on that. Ultimately, the results that we produce go out as revised guidelines or resistance alerts from IRAG, the Insecticide Resistant Action Group, if necessary. Thank you very much.